So let's start the session now. So this is week 9 online live session for the NPTEL course on urban utilities planning, water supply, sanitation and drainage. The course instructor is Dr. Devapratim Pandit. He is a professor in Department of Architecture and Regional Planning at IIT Kharagpur, and I am the teaching assistant for this course. I am Vaibhav Kabadwal. I am a research scholar in the Department of Civil Engineering at IIT Madras. So in this week 9 lecture, we will study about sewer design. So let's start. So uh, for the design of sewer, how to decide which sewer material to choose? So what are the factors which decides the sewer material? Which factors to be considered? So the factors are: it should be resistant to corrosion. First, then it should be resistant to abrasion. Resistant to abrasion. There are two terms, abrasion and attrition. Abrasion is due to two different materials and attrition is due to the rubbing of two similar kind of materials. So it should be resistant to abrasion. So the abrasion means it will contain some solids. So these solids may erode the sewer material. Erode the sewer material. And it should be strong and durable. Strong and durable. Apart from that, it should be preferably lightweight. Preferably lightweight. So that ease of transportation, for ease of transportation. And then it should be impervious. Should be impervious. And it should be low cost. Have low cost. And apart from that, should be hydraulically efficient. Hydraulically efficient. So these factors we should consider while deciding the sewer material. So network of sewers in the community. So the networks are, these are like, first we have sewers in the building. These are called building sewers. Building sewers. Then we have lateral sewers. Lateral sewers, or these are called building connections. building connections. Then we have branch sewers. Then we have main sewers, which will connect two or more branch sewers. Two or more branch sewers. Trunk sewer. And then we have, then they will either discharge to STP or outfall. So we can say them like these are house. So if you have this house, so you have will have these sewer pipelines from these households. You will have lateral sewers. These are called building sewers. Building sewers. These are called lateral sewers. They are called building sewers. They are called lateral sewers. And after lateral sewers, we will have lateral sewer will actually connect to the branch sewer. This is branch sewer. This is branch sewer. And this branch sewer will then connect to the one big main sewer. This is called main sewer. Main sewer then transfer the content or sewage to the trunk sewer. This is trunk sewer and it will discharge either to STP, STP or outfall. This is the network of sewers in the community. This is main sewer. These are laterals. Now we can move on to the next question. What are the different forces acting on the sewers? So sewers can have different type of forces. Sewers are generally circular uh, in shape, in like size, and they are cylindrical in three. If we consider them as a 3D figure, they are cylindrical in shape. Cylindrical in shape. So they can have internal pressure. So when running full, generally sewers are not designed for running full, but due to some uh, overflow, overflow, or they can they may run full and can cause internal pressure. So that's why sewers are in general not designed to run full, but due to overflow or due to unforeseen circumstances, it may run full. So we have to provide the provision. Uh, so we need to have sewer material of such strength that it can bear the internal pressure. So it should bear the internal pressure due to the uh, full flow. Second type of force is pressure due to external load. Pressure due to external load. So sewers are, we discussed in the last class. This is the ground ground level. Here we can have here we can have vehicles, and we can have water lines. Water lines are above. These are water supply lines. These are water supply lines, and we have sewer lines below this. So these are sewer lines. So sewers. So these sewers have to. So this is a load. This is due to the earth pressure, soil weight, plus this is the vehicle load. So sewers have to carry soil weight plus vehicular load. So sewers has to be designed. Sewer pipelines need to be designed to take external load because of the soil weight and the vehicle movement. We have one more, we have two more stresses. These are flexural stresses. So what are flexural stresses? So in the solid mechanics we studied, if you place a beam with some load, it will bend like this. Not exactly like this, but very little. So it will bend. Likewise, if sewers are placed above ground over piers, supports, or trestles, they undergo flexural stresses. So the sewer pipelines, they can bend. They can bend, and here cracks may develop. That will reduce its life. So that's why they should be designed to take the flexural stresses if they are placed above the ground. So we have one more stress, that is temperature stress. Temperature stresses. So when sewers are placed above the ground, they undergo temperature change. during day and nights, during summers and winters. So they undergo change in the temperature, and that temperature, what will it cause? So during summer and they will expansion, during nights and winters contraction. So this repeated cycles will affect the material, and the life of the material will reduce. So that's why the sewer material should be such that it can bear the temperature variation during day and night, and summers and winters. What are the different shapes of sewers? So we have different shapes are these: standard egg-shaped sewers, modified egg-shaped sewers, horseshoe sewer section. This looks like horseshoe. Horseshoe. This is parabolic section. This is semi-elliptical section, rectangular sewer, U-shaped section, semicircular section, and basket handle section. And there is one more which is most important, is circular sewer. Circular sewers. So now we will understand about hydraulic properties of uh, circular sewer. So this is the diameter of the sewer. This is D. This is the flow depth. Dia of sewer. Depth of flow in sewer. Alpha is the this is alpha. This is alpha by 2. This was D by 2. This is alpha by 2. So we can write these sections as O, A, B, this is C, this is D. O, A, B, this is C, this is D. So first we will calculate depth of flow. Which is D. So depth of flow we can calculate it as this total minus, will subtract this D by 2 and minus this OC. This D will be equal to D minus D by 2 minus OC. OC. This is OC length. So this OC is equals to D by 2 cos alpha by 2, and CB is equals to D by 2 sin alpha by 2. So if I write it like this, D minus D by 2 is D by 2, OC is D by 2 cos alpha by 2. So here I can write it as D by D is equals to 1 minus cos alpha by 2 divided by 2. This is the expression for the depth of flow. Now we will derive it for area of flow. Area of flow here is this is the area of flow. So remember two things. This is called sector and this is called segment. These are the two things we need to consider. This is sector, this is segment. So the area of sector first we'll calculate, then we'll calculate, then we subtract this area of triangle, and then from this sector, this triangle if we subtract, we'll get the segment. The area of flow is area of sector minus area of this triangle. Okay, so the area, so total area is when alpha is 360 degree, area is A, which is pi by 4 d square. When alpha is alpha degree, area is A, how much? Not A, it's A dash. This is area of sector. Area of sector. A dash is pi by 4 d square into alpha by 360 degree. And area of flow is will be area of flow means area of segment. Area of flow is area of sector. Area of sector is pi by 4 d square into alpha by 360 minus area of triangle. So this whole width, this will be half into base. Base is how much? Base is AB into half into AB into OC. So let's write here one more thing. AB is how much? AB will be D sine alpha by 2. Half into AB into OC. Half into AB into OC. So it will come out as half into AB will be D sine alpha by 2 and OC will be d cos d by 2 cos alpha by 2. Pi by 4 d square into alpha by 360 minus it will be d square by 4 sin alpha cos alpha. So I will multiply it by 2 divided by 2 and I will multiply it by pi divided by pi. So this will be a alpha by 2. And this area of flow, that is area of segment, is small a. A into alpha by 360 minus a sin alpha by 2 pi. This is small a. Small a by capital A is alpha by 360 minus sin alpha by 2 pi. This is the area of flow. Third, we will understand about perimeter. A, B, C, it is D. So perimeter will be this much. The perimeter. So total perimeter is P is pi d. For alpha is equals to alpha degree, small perimeter will be pi d alpha by, this is angle total alpha by 360 degree. So small p by capital P will be alpha by 360 degree. Then now we'll calculate hydraulic mean depth of flow. That is R. Hydraulic mean depth is area of flow by wetted perimeter. So this can be calculated like R by R. This R means when it is flowing full. This when it is flowing partial. So R is equals to small a by small p, capital A by capital P. It can be written as small a by capital A and small p by capital P. So it will come out as alpha by 360 degree minus sine alpha by 2 pi divided by alpha by 360 degree. This R for full. Receiver is flowing full. Fifth is velocity of flow. So we know the velocities can be written in the form of Manning's formula. V is equals to 1 upon n r to the power 2 by 3 s to the power 1 by 2. So n actually varies with the depth, but we are assuming it as constant. In general, n varies with the depth, but assumed as constant because there is not much change, and depends on the and depends upon the pipe material. V by small v is equals to R by capital R to the power 2 by 3. That means V by capital V is equal to alpha by 360 minus sine alpha by 2 pi divided by alpha by 360 divided to the power 2 by 3. So this is the velocity of flow. Similarly, we can calculate as area rate of flow. Rate of flow. Rate of flow, or we can say discharge. So that is Q by capital Q. when flowing full at depth. So small a by capital A is area. Area is sine alpha by 2 pi into alpha by 360 degree minus sine alpha by 2 pi divided by alpha by 360 degree to the power 2 by 3. So this is q by q, small q by capital Q. So this is q by q value, and we have two little things which is maximum velocity of flow. So for getting maximum velocity, we will at what angle we will get the maximum velocity, that we need to calculate. So small d by capital D, oh sorry, d by small v by capital V divided by d alpha. We will differentiate it and we will put it equal to 0. So we will get some alpha. That alpha, you will get it as 256 degrees, and t you will get it as 0.81 of d. This is for maximum velocity. And for maximum discharge, similarly you can calculate maximum discharge. We will keep d q by q with respect to alpha is equals to 0. Q max. So you will get alpha as 308 degrees and d by d is, you will get d as 0.95 of t. So it is here to show that the maximum velocity is not at the full depth of flow, but it is at this depth, and the maximum flow is not at the full depth, but it is at 0.95 of the dia. So these are the Vmax and Qmax. Now we can solve some MCQs and all. Considering the following data on sewer, the sewer is laid at, the slope is 1 by 400 and the diameter of sewer is 160 mm. The dia is 160 mm. Sorry, 1.6 meter we can write. N is 0.015. So the Manning formula we have to use, and that the sewer is running half full. Even though the sewer runs half full or uh, fully at full depth, so the R will be A by P. So the R we are talking about our hydraulic mean depth. R will not change even though R is equals to A by P. So it will be D by 4 at full depth or half depth of flow. So the velocity of flow in the sewer will be V is equals to 1 by N R to the power 2 by 3 S to the power 1 by 2 and N value is 0.015 R is D by 4, that is 1.5 divided by 1.6 divided by 4 the power 2 by 3. Slope is 1 by 400. Power 1 by 2. So solve it. we are getting velocity as 1.81 meter per second. So no MCQ is correct. Second question is, what is the discharge through the sewer? So we need to calculate discharge. The discharge is area into velocity. So sewer is running half full. So the area, so discharge is, rather, I will try to write it as 514 t square divided by 2. Velocity is 1.81 meter per second. That is pi by 8. What is dt is 1.6 square into 1.81. So I divide by 8 into 1.6 square into 1.81. The discharge which we are getting is 1.82 meter cube per second. Now let me check once more. 5 divided by 8. Yeah, we are getting discharge 1.82 meter cube per second. We have one more question. This is similar. A circular sewer of diameter is 0.6 meter and the slope is 1 into 50. Right? The Manning's coefficient is 0.015. The flow is full actually. What would be the velocity and discharge of the flow in meter uh, per second? So we'll just calculate velocity and then we can calculate. P is equals to 1 upon r to the power 2 by 3 s to the power r to the power 2 by 3 s to the power 1 by 2. So it is n is 0.015 into r to the power r is d by 4, that is 0.60 divided by 4 to the power 2 by 3 and s to the power 1 by 2. Two by 3, 2, 1 divided by 250. Velocity comes out as 1.19 meter per second. answer is B. And discharge we can calculate it as area into velocity. Which formula is used to estimate the self-cleansing velocity? So for self-cleansing velocity we use shield formula. The shield formula is used for self-cleansing velocity. So the particle size and specific gravity. So the water has specific gravity 1 and the particle size is the specific gravity is 2.4 to 2.65. So the conduit, so this is the formula which is given by shield. Which sewage system is depicted in the figure below. So only one pipeline is going to the manhole. So there is no separate thing, so it is combined system. What is meant by return of a storm event? So return of a storm means after how much time that storm may reoccur, means recurrence. So the average recurrence interval between storm events equal to or exceeding a specified value. Duration of the storm, no, this is not correct. Time taken by the storm to return to the rivers or lakes, no, it can be any other thing. Time required for rain falling on the most remote point of the catchment to the flow across a ground surface along a place, no. A is the correct answer. Why sewers are not designed to run full? So the sewers are not designed to run full because extra water may come due to rainfall. So to cater that, the sewers are not designed full, because if extra water comes, so that can be accommodated in the above part of this uh, sewer section. So that's why these are not designed for full flow depth. And apart from that, it can channelize a gas flow. Gas flow can be channelized. So that's why the sewers are not designed to run at full depth. And if we design them for full depth, then it during the rainfall it can cause extra pressures on the sewers and the sewers may burst. That's why sewers are not designed to flow at full depth or full flow or full depth. So this was about the week 9 session. Thank you.